Welcome to Pharmaceutical Calculations, a conceptual approach, Lesson 3, Error Assessment of Drug Dose in Pharmaceutical Mixtures. Today's objectives are all about mixtures. We are going to learn how to calculate the maximum potential error associated with the measurement of any component in a mixture, determine the required SR of any of the balances used to measure the components of a mixture, and determine the least allowable weight of the drug or any other component in the mixture. We do that because pharmaceutical dosage forms are composed of drug and excipients. It's never the drug alone. And in Lesson 2, we have learned how to calculate the maximum potential error associated with a single measurement using equation 1.5, where the desired value here is not the desired values. Now, so the question is, how would you determine the potential error associated with drug dose in pharmaceutical dosage forms where we have mixtures if their preparation involves weighing multiple ingredients on multiple balances of different sensitivity? Remember that every measurement carries a distinct error, and at the end you're going to mix all the ingredients to form a mixture, and the question is how the individual errors propagate within the mixture. To address this problem, we developed a special equation here, which essentially this F here is the drug concentration. It expresses the amount of drug X in a mixture. Y and Z are individual components of the mixture, excipients, let's say. To assess the uncertainty of drug concentration in a mixture, you need to take the total differential of equation to 1, and this can be achieved simply by taking the partial derivative of each component. So basically, you vary drug X while you keep Y and Z constant, and then you vary component Y while you keep X and Z constant, and then you vary Z while you keep X and Y constant. When you carry out the algebra, the total differential of equation 2.1 is equation 2.3, and here dF is the absolute error of drug concentration. dF over F is the relative error of drug concentration. And we have discussed these concepts, these parameters, absolute versus relative error, extensively in Lesson 2. And if you haven't attended Lesson 1 and 2, I would encourage you to do so. Many of the concepts were discussed extensively in those two lectures. dx, dy, and dz are the sensitivity requirements of the balances that we use to measure the respective quantities x, y, and z. Now for two-component mixture, so if we only have two components, the drug and one of the excipients, equation 2.3 is reduced to equation 2.5. N here is basically the number of all ingredients except drug X. So for two-component mixture, since we have the drug and only one excipient, N is equal to 1. So here we have 1 minus 1, which is 0. And therefore equation 2.5 for a two-component mixture becomes dF over F is equal to dC over C with respect to drug. And that's equal to the equation 1.5. So basically, DC is equal to the SR of the balance, and C is equal to the desired value of the drug. Now we can use equation 2.3 to determine the maximum potential error associated with the concentration of any component in the mixture, not just the drug, to determine the required SR of any of the balances we use to weigh the components of the mixture, and to determine the least allowable weight of the drug or any other component within the mixture. We can do all three also for the preparation of a stock mixture or a pharmaceutical product. Pharmaceutical product carries an additional error, and we're going to see one example at the end of today's lecture. Let us first learn how to calculate the maximum potential error associated with the drug concentration in a mixture using example 2.1. So here we are preparing this batch, drug X, drug Y, and lactose Each one has a certain quantity. For drug X is 0.5 grams, drug Y is 2.5, and lactose 67 grams. Total amount in the mixture is 70 grams. And drug X is measured on a balance of sensitivity requirement 0.1 grams. Y is measured on a balance of 0.05 grams of sensitivity 0.05 grams. And the lactose is measured on a balance of sensitivity requirement of 1 gram. It's a bigger quantity and we are using a less sensitive balance. To calculate the percent probable error, maximum potential error in the drug concentration, we simply use equation 2.3. Coupled with equation 2.1, we may need this number here. So that would be 0.5 over 70 grams, right? So that would be 0.007 unitless. So in reality, is grams per gram. So it's grams of drug over grams of mixture. So applying equation 2.3, that's my equation there. Now this over C is dF over F, right? Now Y is 2.5, the lactose is 67 grams, and the drug is 0.7 grams. And the SR of the balance I used to measure the drug is 0.01 gram. The SR of the balance I used to measure Y is 0.05, and the SR of the balance I used to measure lactose is 1 gram. Carry out the algebra, and that's 0.037. That's the relative 0.035. This is the relative error. To calculate the absolute error, all you have to do is to multiply this number by times C. And we know that C is 0.007. So we do that, and we end up with an absolute error of 0.245 milligrams. So conclusively, the error associated with drug X concentration in the mixture is 0.007 plus or minus 3.5%. If you have used equation 1.5 to calculate the error associated with drug X in the mixture, you would end up with a 2% error, which is severely underestimated. Now let's take a look of example 2.2, which essentially is asking you to calculate the SR of a balance so that drug X, when we weigh drug X, we are achieving a maximum allowable error of drug of 1%. So this is a very strict range here. We want to have an error in the drug 1%, maximum allowable error. And this is the same quantities as before, but this time the SR of lactose, of the balance that we used to weigh lactose, is 0.1 grams. So we're using a more sensitive balance. Again, the amount of mixture here is 70 grams. So again, you are using equation 2.3, but this time, this is 1% error. So DC over C is 0.01. The amount of Y, the mass of Y is 2.5 and lactose is 67 grams and drug X is 0.5 grams. We need to determine dx. That's the sensitivity requirement of the balance that is used to weigh the drug. So when you carry out the algebra, you end up with an SR of the balance used that is going to be used to weigh the drug, to measure the drug, of having a sensitivity of 4 milligrams. If you choose a balance that the sensitivity of it is greater than 4 milligrams, that the SR is greater than 4 milligrams, you're going to cause a bigger error in the drug concentration in the mixture. So this is nice. I see here capsules. So lastly, we are going to learn how to calculate the maximum allowable error of drug concentration in capsules. So this is the finished dosage form. So here we have again 70 grams of mixture. The sensitivity requirement of balances, this is the SR to measure capsules. This is the SR to measure of the balance to measure drug X. this is the SR of the balance to measure drug Y, and this is the SR of the balance to measure lactose. And we're going to make 280 capsules. Now the total amount of mixture is 70 grams. Dividing by the number of capsules, we end up with each capsule containing 250 milligrams of mixture. If you wish to assess, to determine how much of each component is in each capsule, you can just cross multiply here. So 0.5 grams of drug X is in 70 grams of mixture in each capsule, how much, and that's how you determine each quantity. Now we have identified in example 2.1 the relative error in measuring in drug concentration in the mixture. The difference here is that we are now preparing capsules, and every time at the end you're going to measure that capsule. So that error on a balance, and you have to accept this statement now, is additive to the error that we have calculated before. And of course, this is the proof is already published in the literature, so you can take a look if you wish to. But the error the error associated with the measurement of each capsule is of course calculated using equation 1.5. And this is the SR of the balance used to measure each capsule, and this is the weight of each capsule. So you have an additional error of 2%. So overall, you have a total error associated, total maximum potential error associated with the concentration of drug in the mixture equal to 5.5%. At this point, I would like you to work on the exercises. I've also included the answer, so you know where to stop. And we have a total of 3 exercises. I would like to thank you for your attention. Until next time.